Hello. Hello, my sweet little gumdrop. This is Quasipup, and welcome to Creative Coping, a place to hang out as we cope our way to the stars. Today we're coping with a little help from this book. This book here. Quantum Theory, a graphic guide. It's pretty cool. It's fun. Or at least from what I've seen. From what I've seen so far, it's pretty fun. Looks like my mic is up a little too loud. Turn it off. Or let me see. All right, I'm looking at like my browser audio and my desktop audio, and they are both really kicking it. Like, I don't know which one is which. Browser. Well, it should be that one. I'm just gonna check and make sure everything is okay as far as audio and all that junk before I get started, because I don't want to find out halfway through that, find out halfway through or all the way at the end that the audio sucked the whole time. All right, I'm just gonna check this real fast. Oops. All right. It's like, okay. Yeah, it looks like. Okay. Yeah, it looks like. I keep forgetting to turn down the mic when I do that. Or turn down my phone. All right. Yeah, it looks cool. I don't know if the music is up loud enough. Okay. We're just gonna leave it like that. Alright, why don't we get started? So this is Quantum Theory, a graphic guide. First time I've tried doing anything like this on stream, but it is a variety stream, so here we are. Oh, right. It is by JP. Hold on, can we see here? There we go. JP McAvoy and Oscar Zarate. 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 Okay, here we go. So, what is quantum theory? I think I'll read and then I'll show the pages like they do with kids. or maybe, I don't know, let's see. What is quantum theory? Quantum theory is the most successful set of ideas ever devised by human beings. It explains the periodic chart of elements and why chemical reactions take place. It gives accurate predictions about the operation of lasers and microchips, the stability of DNA, and how alpha particles tunnel out of the nucleus. That's a lot of inside baseball there. All right, first we've got Einstein. Can we focus? There we go. As Einstein there. Quantum theory is non-intuitive and defies common sense. That's interesting. Then we've got Pauli. I'm going to look up who that is, but let's read what he says first. Recently, its concepts have been likened to Eastern philosophy and used to probe the secrets of consciousness, free will, and the paranormal. Huh. Alright, so there's some people that see it as something that has to do with the paranormal. Pauli, who is that? Well, it'll probably tell us later. Honestly, it's not just going to give us last names, and then it's probably doing that because we're going to see more later. Let's go like this. Alright, let's make sure you can see what I see. And then we've got Dirac on the right there. This is awkward, but it's an experiment. It's a variety stream, so I want to do different kinds of things that strike my fancy. And after, as stupid as it probably sounds, watching Oppenheimer like 3 times in a row kind of got me really interested in quantum theory and quantum physics, and it's just all really fascinating, and I kind of wanted to learn a little bit about it. So my partner got me this little book. It's just a little book. It's just a little one. It's how many pages? 173 pages. It's not very much at all. But here we are. We've got Dirac. Focus. Focus. Here we go. This book answers the question, where did quantum theory come from? Alright, I'm gonna see. And then we've got this guy here. Oh, Schrodinger. Is that what Schrodinger looks like? Quantum theory has never failed, he says. Planck. Quantum theory is essentially mathematical. Born says its structure has revolutionized how the physical world is viewed. And then we've got Niels Bohr at the bottom. Or Niels Bohr. De Broglie, I don't know who that is. And Heisenberg, everybody has some idea who that is, thanks to a certain show. Alright, so it says at the bottom here, Niels Bohr's presentation of quantum theory in 1927 remains today's orthodoxy. But Einstein's thought experiments in the 1930s questioned the theory's fundamental validity and are still debated today. Could he be right again? Is there something missing? Let's start at the beginning. And then we've got our next page here. Introducing quantum theory. I'll start with the bubble up at the top left. He says, you can see for yourself. Whoop, there we go. You know, it's easier to explain quantum theory to an absolute beginner than a classical physicist. I really hope that's true, because that's what I am. We've got all these physicists, I guess, back there. You're kidding. What's their problem, these classical guys, with the modern theory? So the classical guys in the modern theory. Bottom text. The problem is this. Just before the turn of the century, physicists were so absolutely certain of their ideas about the nature of matter and radiation that any new concept which contradicted their classical picture would be given little consideration. Let's hold it up here. Let's see. Not only was the mathematical formalism of Isaac Newton, 1642 to 1727, and James Clerk Maxwell, 1831 to 79, impeccable. So not only was the mathematical formalism of Isaac Newton and James Clerk Maxwell impeccable, but predictions based on their theories had been confirmed by careful detailed experiments. Not carefully detailed experiments? Or just careful detailed experiments. For many years, the age of reason had become the age of certainty. And we've got our next page here. Classical physicists. He looks... Look at him. He kind of looks like... I don't know. Let's not be dumb. Let me see. What is the definition of classical? By classical is meant those late 19th century physicists nourished on an academic diet of Newton's mechanics and Maxwell's electromagnetism, the two most successful syntheses of physical phenomenon in the history of thought. That first sentence really, by classical is meant those late 19. Nah, it probably makes sense. Let's see. And then we've got his speech bubble here. With a simple inclined plane and a metal sphere, I demonstrated that the great Aristotle's physics was flawed. Oh, stop showing off. He says there. Testing theories by observation had been the hallmark of good physics since Galileo, 1564 to 1642. He showed how to devise experiments, make measurements, and compare the results with the predictions of mathematical laws. And our very bottom text we've got here, all the way at the bottom. The interplay of theory and experiment is still the best way to proceed in the world of acceptable science. Theory and experiment. So I'm probably going to go through this for about an hour. And then we'll call it quits for this stream. Maybe. I don't know. Unless I want to keep going and we get to a really good part. Alright, so we got our next pages here. Boop. Let's see. I guess I could hold it like this. During the 18th and 19th, well, at the very top of the left page, it's all proven and classical. During the 18th and 19th centuries, Newton's laws of motion had been scrutinized and confirmed by reliable tests. My gravitation law has been used to predict measured movements of the planets with great accuracy, he says while floating on like asteroids or something. Let's see, we've got a text bubble down here. Oops. My scene. And this is Toasty, by the way. Say hi, Toasty. Hi. Hey. Whoa. Toasty. I predicted the existence of invisible light waves in my electromagnetic... Let me see. My electromagnetic wave theory of 1865 and Heinrich Hertz, 1857 and 94. Wow. Like 50. Detected signals in 1888 in his Berlin laboratory. Now they're called radio waves. So... These... Oh, my fez. These waves reflect and refract just like light. Maxwell was right. No wonder these classical physicists were confident in what they knew. This might not be the best book to read, but again, it's an experiment. I don't know, it's kind of cool. It's got cool art. It's got fun art. I don't know. Fill in the sixth decimal place. A classical physicist from Glasgow University, the influential Lord Kelvin. Oh, Kelvin. I know something about Kelvins. That like... Oh, I can almost remember what a Kelvin is. Is it 470 or 37? I don't know. I'm going to look it up. I'm going to look up what a Kelvin is. What is a Kelvin? How many degrees is that? Base unit thermodynamic temperature and the international system of units. Oh, okay, so the Kelvin scale. Kelvin's scale is absolute, meaning it starts at absolute 0. Or infinite cold, where there's no thermal energy. A change of 1 Kelvin is the same as a change of 1 degree Celsius. Oh, okay. Simple enough. Probably. Alright, moving on. Kelvins. Let's see. Right, we're here. Lord Kelvin. Classical physicist from Glasgow University, the influential Lord Kelvin spoke of only 2 dark clouds on the Newtonian horizon, relativity and quantum theory. How was I to know that one of these clouds would disappear only with the advent of relativity, and the other would lead to quantum theory? It says here. Kind of weird because I've got my camera angled a little bit because of how I'm sitting. Where I'm sitting as opposed to how my desk is angled. Alright, what do we got next? Maybe I should get rid of... Let's get rid of the logo here. There we go. And I think that's it. Okay. Here we are. In June 1894, the American Nobel laureate Albert Michelson, or Michelson, probably Michelson, 1852 to 1931, thought he was paraphrasing Kelvin in a remark which he regretted for the rest of his life. All that remains to do in physics is fill in the 6th decimal place. I can't believe I said that. It's that guy there. Albert Michelson. 6th decimal place. So he thought that was all there was to it. That's all there was left to figure out. It's wrong. He was wrong. Absolutely wrong. Alright, oh, and we've got a picture. Oh, there's Einstein, I believe. We've got an actual picture. Yeah, I think that's Einstein right there. Got all these folks here. All of these folks that have something in common. Let's see. They are physicists and scientists. Fundamental assumptions of classical physics. I'm just going to read this one without... There's not too much art going on here. Classical physicists had built up a whole series of assumptions which focused their thinking and made the acceptance of new ideas very difficult. Here's a list of what they were sure about, or what they were sure of about the material world. So 1, the universe was like a giant machine set in a framework of absolute time and space. Complicated movement could be understood as a simple movement of the machine's inner parts, even if these parts can't be visualized. The Newtonian, and then the second one. Number 2, the Newtonian synthesis implied that all motion had a cause. If a body exhibited motion, one could always figure out what was producing the motion. This is simply cause and effect, which nobody really questioned. If the state of motion was known at one point, say the present, it could be determined at any other point in the future or even the past. This is number 3, by the way. I really need to get better at doing that. Let's see. So if the state of motion was known at one point, say the present, it could be determined at any other point in the future or even the past. Oh yeah, that makes sense. It's kind of like those word problems, you know, if a train is moving this fast to Oklahoma and this other train is moving this fast in the opposite direction, then when will they cross paths? You know. Or when did they cross paths? Or will they ever cross paths? Let's see. It could be determined at any other point in the future, even the past. Now, nothing was uncertain. Only a consequence of some earlier cause. This was determinism. Okay. Let's see. Number 4. The number 4 assumption of classical physics. It's right up top there. Why don't you read it to me? Go ahead. Come on. No? Okay, I'll read it. I'll read. The properties of light are completely described by Maxwell's electromagnetic wave theory and confirmed by interference patterns observed in a simple double-slit experiment by Thomas Young in 1802. Number 5. There are 2 physical models to represent energy and motion. One, a particle, represented by an impenetrable sphere like a billiard ball, and the other a wave, like that which rides toward the shore on the surface of the ocean. They are mutually exclusive, i.e. energy must be either one or the other. Either... right towards the shore. So there are 2 physical models. So either a particle or a wave. It is possible to measure... Number 6. It was possible to measure to any degree of accuracy the properties of a system. Like its temperature or speed, simply reduce the intensity of the observer's probing or correct for it with a theoretical adjustment. Atomic systems were thought to be no exception. Classical physicists believed all of these statements to be absolutely true, but all 6 assumptions would eventually prove to be in doubt. Some obnoxious people outside. The first to know this... Excuse me. A little indigestion. Weird. Okay. So... all 6 assumptions will be proved to be in doubt. The first to know this were the group of physicists who met at the Metropole Hotel in Brussels on 24th of October, 1927. And I guess that's all these guys. All these guys down here. Let's focus. Maybe you recognize some of them. And all these guys. You got Einstein there. It's the only one I recognize. Okay. Alright, so now we have come to the Solvay Conference, 1927. Formulation of quantum theory. This is still really dry. Still really, really dry. A few years before the outbreak of World War I, the Belgian industrialist Ernest Solvay, 1838 to 1922, sponsored the first of a series of international physics meetings in Brussels. Attendance at these meetings was by special invitation, and participants, usually limited to about 30, were asked to concentrate on a prearranged topic. The first five meetings held between 1911 and 1927 chronicled in a most remarkable way the development of 20th century physics. The 1927 gathering was devoted to quantum theory and attended by no less than 9 theoretical physicists who had made fundamental contributions to the theory. Each of the 9 would eventually be rewarded a Nobel Prize for his contribution. So we've got Archimedes, the top left, Newton, bottom left, Kepler, Galileo, next to Newton, Faraday, and Maxwell. And it seems like they are all meant to be saying it is comparable to seeing us posing together to commemorate the development of classical physics. Let's see, and this is regarding the photograph that was on the previous pages, and they kind of show it again. This photograph of the 1927 Solvay Conference is a good starting point for introducing principal players in the development of the most modern of all physical theories. Future generations will marvel at the compressed time scale and geographical proximity which brought these giants of quantum physics together in 1927. There's hardly any period in history of science in which so much has been clarified by so few in so short a time. Yeah, you get them all together and get all those brains in the same room. Oh, wait. I think there's a woman here. Holy shit. No, pardon my language. But yeah. Who is that? Wish there were like names for each and every one of them. You know, put a name there, put a name there, put a name there, put a name here. Alright, so this guy here, maybe we'll find out who that is. I started it all in 1900 by postulating that matter can absorb and emit electromagnetic radiation, i.e. light, only in energy bundles called quanta, whose size is proportional to the frequency of the radiation. Oh wait. I skipped a bit. So I'll go back to the top here. Let's see, quantum physics together, so short a time. Look at the sad-eyed Max Planck in the front row next to Marie Curie. That's who that is. So we've got Max Planck here. Focus. And Marie Curie. Hey. Let's see. Right. And with his hat and cigar, Planck appears drained of vitality, exhausted after years of trying to refute his own revolutionary ideas about matter and radiation, because that's how science actually works, right? You come up with something and you try to disprove it. I just heard that or saw that recently somewhere. It's not about trying to prove something, it's about trying to disprove it. Something like that. Let's see. Okay, next page. Alright, we've got this picture of these guys again. Okay, it looks like they are kind of going through and telling us who's who. Who's that? Polly. Alright, let's see here. So we're on to the next page. We've got them again. And we've got some text at the top on the left. A few years later, in 1905, a young patent clerk in Switzerland named Albert Einstein, 1879 to 1955, generalized Planck's notion. That's Einstein in the front row center, sitting stiffly in his formal attire. He had been brooding for over 20 years about the quantum problem, without any real insights since his early 1905 paper. All the while, he continued to contribute to the theory's development and endorsed original ideas of others with uncanny confidence. His greatest work, The General Theory of Relativity, I think most of us are familiar with that one, which had made him an international celebrity, was already a decade behind him. So we've got Einstein saying some things here. What are you doing? Okay, got a cat on my shoulder. So there's Einstein chatting. Gabbing. I showed that light always exists as quanta, which is, of course, why matter absorbs and emits it as such. Too bad Planck never believed me. Really? Alright, top of the next page. In Brussels, Einstein had debated the bizarre conclusions of the quantum theory with its most respected and determined proponent, the Great Dane Niels Bohr. Or is it Niels Bohr? 1885 to 1962. Bohr, more than anyone else, would become associated with the struggle to interpret and understand the theory. At the far right... Oh, it's going to sheets. Far right of the photo, in the middle row. They can't hear you from there. Let's see. At the far right of the photo, in the middle row, he's relaxed and confident. The 42-year-old professor at the peak of his powers. Alright, so we've got... Is that Niels Bohr on the right there, then? Ooh, there we go. In my lecture, I reviewed the probabilistic interpretation of quantum theory to the apparent satisfaction of mostly everyone except Einstein. My lecture, I reviewed probabilistic. Oh. Thus began a running argument between these two masters of 20th century physics, lasting up to Einstein's death in 1955. Well, they never agreed up until he died. And then there's no more agreeing after that. Whoa, jeez. Where am I? Okay. Let's see. Next page. Got a big old block of text at the top. Let's see if we can get you in here. There we go. Maybe you can read along. In the back row behind Einstein, Erwin Schrödinger, 1887 to 1961, looks conspicuously casual in his sports jacket and bow tie. And then we've got to his left, but one are the Young Turks, Wolfgang Pauli and Werner Heisenberg. Let's see, I'm gonna skip their birth and death dates. Still in their 20s, and in front of them, Paul Dirac, Louis de Broglie. This name. Hold on. That one. Seems like maybe it's French. Max Born and Bohr. These men are today immortalized by their association with the fundamental properties of the microscopic world. The Schrödinger wave equation, the Pauli exclusion principle, the Heisenberg uncertainty relation, the Bohr atom, and so forth. They were all there with Planck, the oldest at 69, who started it, who started it all in 1900, to Dirac, the youngest at 25 years, who completed the theory in 1928. Okay. Alright, just gonna read a little bit more of this. Maybe we'll get to page 20. This is super dry. Alright, the day after this photograph was taken, 30th October 1927, with the historic exchanges between Bohr and Einstein still buzzing in their minds, the conferees, I've never seen that word before. I know what it, it's obvious what it means, but boarded trains at the Brussels Central Station to return to Berlin, Paris, Cambridge, Göttingen, Copenhagen, Vienna, and Zurich. So let's see. Yeah, we've got an image of everybody leaving Brussels. They were taking with them the most bizarre set of ideas ever concocted by scientists. Secretly, most of them probably agreed with Einstein that this madness called quantum theory was just a step along the way to a more complete theory and would be overthrown for something better, something more consistent with common sense. I don't like common sense being used as a phrase. but that's what's in the book, so. All right. But how did the quantum theory come about? What experiments compelled these most careful of men to ignore the tenets of classical physics and propose ideas about nature that violated common sense? Again, common sense. Before we study these experimental paradoxes, we need some background in thermodynamics and statistics, which are fundamental to the development of quantum theory. So, what is thermodynamics? The word means movement of heat, which always flows from a body of higher temperature to a body of lower temperature, until the temperatures of the two bodies are the same. This is called thermal equilibrium. Heat is correctly described as a form of vibration. Oh god. And then we've got this at the bottom here. This seat is warm. Did you leave something thermal behind? No, it's just that the molecules in the seat are still vibrating at the same rate as my body, which is apparently faster than yours, so the seat feels warm to you. That's very interesting. So it's vibration. So as you sit there, eventually it'll start vibrating the same. Or if you hug somebody who's colder than you, I guess, will your vibrations match up then? Same rate as my body, which is apparently faster than yours. No. Well, I don't know. I'm gonna look that up. Look up whether... Can two people... Can two people sharing heat... Do they wind up vibrating at the same frequency? Two people begin to vibrate at the same frequency. Let's see. No. When sharing heat, two people of any object with different temperatures and begin to vibrate at the same frequency in the way that two musical instruments might resonate. Is it me, or does heat go up in a room when being together with a... Okay, this is bringing up like soulmates and stuff like that. That's not the direction I was going in. Alright, let's move on. Where were we? Right, the weird seat thing. Alright, so we've got the next page. First law of thermodynamics. And maybe this is where we'll end for today. First law of thermodynamics. Mechanical models to explain the flow of heat developed quickly in 19th century Britain. Building on the achievements of James Watt, 1736 to 1819, a Scot who had built a working steam engine. And here's kind of looks like here's a diagram of the steam engine itself. Right there. Soon after, the son of Manchester brewer, James Prescott Joule, 1818 to 89, so 781, showed that a quantity of heat can be equated to a certain amount of mechanical work. This new mechanical equivalent of heat was the beginning of the study of thermodynamics, and that's our man there with the beard saying that. Let's see, then somebody said, since heat can be converted into work, it must be a form of energy. The Greek word energy means containing work. But it wasn't until 1847 that a respectable academic scientist, Hermann von Helmholtz, 1821 to 94, stated, right down here, whenever a certain amount of energy disappears in one place, an equal amount must appear elsewhere in the same system. So first law, got work, heat, and energy. I don't know. Let's see what you make of this. We've got this equation here, or this diagram. Can we see it? Come on. There we go. Yeah, that. So this is called the law of conservation of energy. And I think we all know something about that, right? Energy is not created or destroyed. It only changes states, right? Something like that. It remains a foundation of modern physics, unaffected by modern theories. Okay, that was a nice little experiment. We're gonna stop for now. It's like 45 minutes or so. So, let's see. I'll be back tonight for some more 7 days to end with you. Until then, it was nice learning something with you. It's nice learning something with you, and I will see you later. Later. And logo 2. See you next time.